We have three, as I mentioned, three very useful talks, very relevant talks. So I'm going to turn it over to Suzanne to talk to us about the subsea desalination. You can now share your screens, Suzanne, and start your presentation.
Thank you all for having us and listening to us and for giving us the opportunity to work with you. As Ram said, I'm Suzanne Chess and I'm Managing Director and Spokesperson for Tiabzu. Also here with us are some of my team members, Dr. Tim Forstman, Dr. Dan Tormey, who you've heard a bit from, who's with Catalyst Environmental Solutions, our regulatory advisors. Mike Edwards and Bob Evans will be presenting with me, and Ryan Elliott, our subsea engineer, will be joining shortly. That brings us to Tiabzu, which brings the tools, technology, and techniques to change the environment for desalination. It leverages natural processes of deep ocean hydrostatic pressure for reverse osmosis, relative density between freshwater and saline seawater for buoyancy control, and a symbiosis with existing offshore infrastructure to make subsea desalination competitive. 40% of the energy required for coastal desalination is for multi-pump pre-osmosis. This can be reduced, if not eliminated, by operating below ocean's most biologically productive zones. And this also removes the environmental impact of intake and discharge accumulation on phytoplankton, the marine carbon cycle, potential negative feedback on climate that disruption of these systems can cause. This is expected to confer regulatory advantages for pilot and post-pilot scaling.
Hi, I'm Bob Evans. First of all, I'd like to give Suzanne a flower this morning for her hours and effort on this project. And our wonderful team that we put together in the last 6 years. A real quick story. When we first started this project, we met with Ryan Elliott to run the numbers on this concept that I had come up with. And we met in Santa Barbara during the drought on a blue sky, and we're sitting outside, and Ryan hands a piece of paper to me to look at. And out of the blue, this white cloud appeared above us, and it started raining. And I told Ryan, don't touch that piece of paper. And it got wet from the raindrops coming down from the sky. So at the age of 16, I was photographing California fishing game reefing of their streetcars off of Palos Verdes. Repurposing cars, tires, and bowls became lobster hotspots. I went on to photo document abalone and scallop habitats on platform Holly and Hope. These aquaculture projects during the 1970s were the first alternative uses for platforms. In 1976, I co-founded the Mussel Company to commercially harvest mussels for human consumption, a joint project with NOAA and Chevron on platform Hilda that established the California mussel industry. It took us 5 years with different agencies to make this happen. Exxon had been following our work in the Santa Barbara Channel. Their director of public relations, D.I. Bolding, invited us to conduct a 3-year study documenting the marine life as it developed below its newly installed platform Hondo, which was an 850 feet off of the Gaviota coast. Eventually, I got tired of hand tending 500 feet of umbilical, my design, and I asked the mechanical engineering department at UCSB to find me some students to develop my design for electronically controlled buoyancy control system. Our first expedition was filming the second largest natural oil seep in the world off of Coal Oil Point. Our monitor revealed a moon-like surface with circular holes releasing oil and gas. The project merited John and Hugh a prestigious award. Innovations in buoyancy control for subsea development and removal from depth are patented methods for Tiabzu and key to its expected success. We had carte blanche from the offshore operators, and I logged 850 dives below the California platforms. After diving in jet fins for years, I decided to make a better fin. To do this, I pioneered the use of composite tooling for polyurethane production, used hundreds of thousands of pounds of polyurethane each year in our US plant. Suzanne and I established an international supply chain and distribution networks for our iconic brand Force Fits. We embarked on Tiabzu, desalinization by reverse osmosis system within a submersible hull. Key components of the desalinization module are its membrane system, RO water receiving tank, umbilical, membrane flush, and extraction pumps. The umbilical connects the system to a surface supply vessel, platform, or shore. The umbilical holds power, communication cables, and a snorkel connecting an RO water receiving tank to the surface. This maintains the tank's internal atmospheric pressure. The difference between it and the ambient seawater keeps water flowing through the RO membranes. A pump extracts purified water from the tank to the surface or shore, or with a switch of a valve into a bladder.
This is Mike Edwards. You might think of the Tiabzu system like a hot air balloon. Instead of using difference in air temperature for lift, its balloon or bladder that you see on top there provides lift using the approximate 3% difference in relative density between the RO water and ambient saline seawater. This integrated buoyancy system facilitates implementation. Tiabzu models can deploy using A-frame or davit. They can also launch from commonly accessible harbor ramps and small tow vessels. The bladder is used for buoyancy control for deployment and for recovery or maintenance or at end of life. During mobile operations, buoyancy is used to drop into position and to maintain at operational depths. This buoyancy system integration is expected to significantly lower capital costs associated with implementation and address the regulatory requirement for removal at end of equipment life. The RO maintenance cycle is 5 years with a 25-year life. In an alternative configuration, the bladder can be filled with enough RO water to be employed to lift objects subsea. Water is non-compressible, more stable, and safer than using airbags that accelerate toward the surface or sink in response to changes in depth and ambient pressure. Heavy lift cranes generally used for subsea deployment and removal projects are in limited supply. They have very high day rate. So competition for these cranes with a myriad of offshore projects requiring their use can cause significant delays, which raises capital expenses. With respect to needing a heavy lift crane to deploy and recover a large desal system, it's enough to tip the scale outside of economic viability. To put in perspective the significance of penciling down prospective costs of implementation, the price for a barrel of crude or equivalent natural gas is probably between $24 and $70 a barrel. Water is less than a penny per gallon for most markets, so it converts to about 42 cents a gallon, or about 42 cents a barrel. There are other variables that offset some of this, such as throughput volume and the non-depleting resource in seawater. We approach repurposing of offshore infrastructure as a collaborative process, working together with owner-operators, leveraging their assets while, without interfering, they continue to operate. This collaboration establishes a framework for development and regulation before momentum for decommissioning takes over. The alternative use provides a transition as productivity depletes, and in the case of Tiabzu, as alternative energy sources come online. It's a transformation that is supportive of a new offshore economy.
If any of you are traveling through Santa Barbara, please have a look at our Marine Megatropolis exhibit that has been up for 2.5 years in the main terminal. It's very relevant. And on behalf of our team, I thank you.
Awesome. That was perfect. I would like to see a few of the RPC members and my own picture at the bottom there where it says you.